All right, so we've done several examples of evaluating integrals using integration by parts. And what I want to look at right now is a kind of a shortcut to those types of integration by parts problems where you have to apply integration by parts multiple times. We've already done one example, two actually, where we've needed to evaluate an integral by applying integration by parts twice. And it can get kind of lengthy and kind of tedious when you have to keep doing integration by parts over and over again until you end up with an answer. So we're going to look at a technique called tabular integration. Tabular meaning having to do with a table. This is also in some texts called the DI method, and I'll explain why that is. And this is a great technique to use when you have to use integration by parts over and over again before getting an answer. So here is an example, okay? I want to evaluate the definite integral of x to the fourth. I think I said definite. I meant to say indefinite integral of x to the fourth e to the 2x. This looks pretty similar to previous examples that we've dealt with. And in fact, this one involves a polynomial, which we have been choosing to be the u and letting the other function, in this case e to the 2x, be the dv. And we talked about why that is, because when you let u be the polynomial term, when you differentiate, or the u term, is that what I said? Oh, yeah, when you let the polynomial term be your u, differentiating it shrinks that power down, eventually shrinking it down to a constant and then 0, which makes it go away, and the final answer is easier to evaluate. What I want to do is make note of a pattern that occurs when we are doing this over and over again. Okay, so let me see if I can find, looking for my second example, I think. I'll shuffle through some papers here until I can find it. Okay, so let's take a look at, I think it was this one right here. Yeah, x squared cosine of x. So notice the first thing that I did is I set u equal to my x squared term, and then v ended up being sine of x because dv was the cosine of x dx here. I ended up with uv as this term right here, right? So the very first thing that I get is uv. But what happens next? I ended up with an integral that was not quite doable without doing integration by parts another time. So I decided to go again with the integration by parts, but this had me choosing a new u and a new v, okay? So in this case, I chose u to be 2x, dv was sine of x dx, so that meant v was negative cosine of x. And notice that the new uv appears here, okay? So here is my old uv, here is my new uv. But this new uv is going to have a negative that distributes to it. So whatever my new uv is, in my final answer, its opposite will show up here. Okay, so here again, old uv, new uv, but made negative. Suppose I had to do this again. Suppose that this wasn't x squared, but maybe it was an x cubed, which would have meant that there would be one more integration by parts step here. By applying integration by parts to the new integral that would have appeared here, I would get another two terms, the first of which is the new uv for that round of integration by parts, and I would have another negative distributing to it. But I've already had this negative to account for, and so a new negative distributing to that is a negative negative, which makes it positive. So what ends up happening, kind of what I'm getting at here, is that when we have to apply integration by parts over and over again, what we end up with is this sequence of terms, each of which can be thought of as one of your UVs. Here's the first UV that we got, the second UV, the third UV. However, the sign in front of that UV is going to alternate between pluses and minuses because of this minus sign that keeps distributing it. So making a note of that pattern in our heads, let's think through what would happen here. I would normally choose u to be x to the fourth so that I could differentiate that to get a du with a smaller exponent. I'm going to create this table here, and I'm going to label these two columns d and I. The d stands for differentiation or derivative. The I stands for integration or integral, or antiderivative is how we're really dealing with that. So whatever I would have chosen to be my u here, in this case x to the fourth, that's going to be the first thing that shows up in this d column here. Whatever would have been dv is going to show up in this one. And for this table, I'm not going to bother writing the dx. We don't need it for this. So I'm going to just say e to the 2x, okay? Now think about this for a second. Remember what I said. When we're doing integration by parts multiple times, what we end up with is a bunch of terms which you can think of as all of these UVs that appeared in each step of that process. So if this is my U that I would have chosen, I don't know why I wrote a 2 there. It should have been a 4. If this was my U, then what would my V end up being? Well, this was dV. So my V is the antiderivative of this, which is 1/2 e to the 2x, okay? Now, if this is my u, what would du have been? I have to take a derivative here, 4x cubed, okay? So uv, the first uv term would have been this guy times this guy, all right? And at this stage in the process, it's just uv. I don't have to take a negative of it or anything like that. So I'm going to put a little plus here to remind me that I'm not changing the sign, okay? Now in the next step, I would have done my integration by parts and all of that, and what I would have ended up with here is a new integral, the integral of v du. And remember, if this was u, then this is my du, and if this was dv, then this would have been v. So my new integral is going to have a product of these two terms, and I can see that that's not going to be helpful because I can't evaluate that without doing integration by parts a second time. So I would choose this to be my next u, and I'm going to differentiate it. That's going to give me 12x squared. This is going to be the new dv, and so I integrate that or take an antiderivative. That would be 1/4 e to the 2x. I can already see that my table's not quite big enough. Okay, now the new, we said this is the u, this would be the new v now, and the new u and the new v are going to get multiplied together. Okay, but we're going to make note of that pattern that we noticed before, and this becomes a negative. We have that minus sign that distributes in. So hopefully you can kind of see a pattern that's going to occur here. In this column, we're going to continue differentiating things over and over again because each new term is going to be thought of as our new u. And in this column here, we're going to keep integrating things over and over again. So let's keep doing that. Let's just fill out this whole table and then figure out what to do with it. I'm going to keep differentiating this. I'm going to get 24x next, and then I'm going to get 24 when I take a derivative of that. That's a constant, so its derivative is 0. That's my indication that I need to stop. Because once I get a 0 there, if I kept doing integration by parts, I'm going to have 0 times something, and that's going to give me just 0. There's nothing more that happens after this. But let's match all of these new values or terms up with the corresponding things in my I column. So I'm going to keep integrating. 1/8 e to the 2x, 1/16 e to the 2x, 1/32 e to the 2x. Those are these continued antiderivatives. And then what's going to happen with these arrows here, which indicate the products that I'm forming? Well, they're going to keep multiplying, but alternating between pluses and minuses. Plus. Okay? So this 0 here, it doesn't matter what would have appeared next because 0 times anything is 0, and that's not going to contribute to our answer. So this is the last product that I have to form. So here's what we have. The integral of x to the 4th e to the 2x is equal to all of these products as a big sum of terms. So x to the 4th times 1/2 e to the 2x. That's going to look like 1/2 x to the 4th e to the 2x minus, remember that minus is there, alternating pluses and minuses. 4 times 1/4 is 1, so I'm going to get x cubed e to the 2x when I multiply these two terms because those constant coefficients cancel each other. 12 times 1/8 is 3/2, so I'm going to get plus, there's a plus there, 3/2 x squared e to the 2x. And then 24 times 1/16 is also 3/2. This is the minus term. This is my alternating terms here. I have a negative now. Minus 3/2 x e to the 2x. Finally, I have plus 24 times 1/32, which is 3/4. So that's 3/4 e to the 2x. And then finally, it's an indefinite integral, so we need to include a plus c. And that's my answer, okay? Now, that took a little bit of time because I was kind of talking through the logic behind it. But now that you know how this technique works, this thing here, which would have required several iterations of integration by parts, can be handled much more quickly by setting this x to the 4th term as my first u, so it's here, and then the e to the 2x term here, and then you just know I differentiate until I get a 0, and then I integrate on this side until I have something that matches each term in my d column, and then I multiply things together using these arrows and alternating signs, and that's it. Altogether, that's a lot less work than it would have been if we had done integration by parts over and over again, okay? All right, I want to do one last problem here, then we're going to wrap up 7.1. Here, what we're trying to do is derive something called a reduction formula. So what is a reduction formula? A reduction formula is where we have an integral, and the integral involves an integrand that might be difficult to evaluate initially, maybe because it has like something like this, a product of two functions. I have an x with a power of n on there. As we saw up here, this is a function that kind of looks similar to what we're seeing down here. I have x to some power and then, you know, an exponential function appearing there. The goal of a reduction formula is to take an integral of this type and represent it using an expression that might have an integral of a similar type, but with a smaller power, okay? So this power, n minus 1, is smaller than that n. So in a sense, the integral that results from using this reduction formula is just slightly simpler than what we started with, only because of the smaller exponent. And then the goal of this is that if n is some integer, you know, say n is like 10, I can apply my reduction formula over and over and over again, shrinking that exponent down by 1 each time until until this exponent shrinks down to 0, eliminating that term here. So it's kind of a formula that can be used as a shortcut for dealing with these sorts of integrals. But what we want to do is show that this reduction formula works. So if I was given an integral of x to the n e to the x dx, we don't know what n is. The assumption is just that it's some constant. I want to perform integration by parts on this to come up with my reduction formula. To do that, I would set u equal to x to the n, because again, that's a polynomial term if n is an integer. If it's not, it's just a power function, but the same idea applies. dv is going to be e to the x dx. This would mean that du, from my power rule, is nx to the n minus 1 dx. That's literally just the power rule that I'm using. My v is just equal to e to the x. When you're doing your homework, maybe give yourself a little bit more space than I'm giving. I'm finding that I'm not planning the amount of space that I have to write these things very well, and I keep kind of getting cramped. So maybe give yourself a little bit more space than I'm giving. According to integration by parts, I would have x to the n times e to the x. I'm integrating that. That would be equal to uv, which is going to look like x to the n e to the x, minus the integral of v du. So that's going to look like n e to the x, that's my, or e to the x times x to the n minus 1. I should have put my x to the n minus 1 there, but I'll put it here for now. dx. Now that n, remember, that's a constant, so I can bring that n out like this. And let me rearrange my terms here. X to the n minus 1, e to the x dx. And notice that's exactly what we were trying to show, that this is equal to this. So that one, there's almost no work really to do. It's just straight from one application of integration by parts. But you're going to see in the homework that there's problems where you're asked to show that a reduction formula that they give you works, and this is the idea. Okay, that wraps things up for 7.1.